Okay, our first fluid mechanics example problem looks pretty straightforward. You gotta make sure you know a couple of things here. Uh, Gauge pressure, rho GH. Rho is the density of the fluid. G is the acceleration due to gravity on planet Earth. And H in this case is going to be the depth, not really the height, but the depth. So 120-gram screwdriver descends to a depth of 30 meters in open ocean where he floats around looking for treasure. The density of the water is 1,025 kilograms per meter cubed. Multiply that by acceleration due to gravity. You can use 10 meters per second. And not the height, but rather the depth. How much height of water is above him? 30 meters. Multiplying all of that together, we find the gauge pressure is 307,500 pascals. Part 1. Part 2, determine the absolute pressure. Well, the absolute pressure is the atmospheric pressure plus the gauge pressure. Don't forget that, yeah, he's got all this water on him, but there's 7 or 8 miles of air also above him. That's the absolute pressure, is the air plus the weight of the water. We've got the atmospheric pressure plus the pressure from the water. So there's both of those combined to make the absolute pressure. Standard atmospheric pressure is just about 10 to the 5th pascals. That's the accepted value. 10 to the 5th pascals, or 100,000, plus our gauge pressure of 307,000. So the absolute pressure is going to be 100,000 pascals plus 307,500 pascals for an absolute pressure of 407,500 pascals. That's the absolute pressure. Now the buoyancy force. Well, that's an interesting one. The buoyancy force. Let's think carefully here. Buoyancy force. Very important. He's floating around. He is not rising or he is not sinking. He is floating at this depth, which tells you that he's not rising or sinking. So if he's not going up or going down, the vertical forces on him are in balance. He's in equilibrium. So his weight down and the other force on him is the buoyancy force. They equate. The buoyant force equals the force of gravity. So the buoyant force is equal to, in this case, because he's floating there, mg, 120 kilograms times g, 10 meters per second squared. The buoyant force upon him is 1,200 newtons. And the last part of this question is determine the density of the diver. Here's a little tricky, getting ahead of ourselves a little bit. You need to know how to calculate the buoyancy force. The buoyancy force is rho v g. And this gets we need to clarify this a little bit. This is the density of the fluid. The volume of the fluid that gets displaced. And this is our every happy 10 meters per second squared. But that's how they calculate that. So now this is the next thing. The last part of the question, the buoyancy force we know is equal to rho v g. 1,200 newtons was the buoyancy force. The density of the fluid is 1,025 kilograms per meter cubed. That's supposed to be cubed, okay, times the volume of the displaced fluid, which would be the volume of our man, and G. 10 meters per second squared. So we take our 1,200, divide that by 125 by 10. The volume of our man is 0.117 cubic meters. Well, we don't know much, but we know enough to figure out the density of the diver. Density equals mass divided by volume. We were told the mass of our man. Density equals mass, 120 kilograms, divided by 0.117 cubic meters. And we get the density of our man to be 1,025 kilograms per meter cubed. Works out pretty nice to be the same density as the surrounding ocean water.